Welcome back, Calculus Wizards. So this section, 1.4b, is all about continuity. So I'm going to try to break down all of these crazy definitions for you. So a graph is continuous at some value, and we're going to say x equals c. That's pretty much what it says, if it's uninterrupted at c. So in other words, I don't have to lift my pencil. And a function is continuous if it meets the following conditions. So f of c is defined. In other words, there's a y value at f of c, and I can find the limit as x approaches c, and that limit as x approaches c happens to equal that defined value. And then a function is continuous on an open interval a to b if it's continuous at every point in that interval. So essentially it's talking about that there's no break in the graph. I don't have a hole, I don't have a jump, I don't have an asymptote. So we're going to look at all those examples of discontinuities below. One more thing that I wanted to mention is if it's continuous on the number line, then of course that domain would be from negative infinity to positive infinity, all real numbers. Okay, so now looking at this first one, these graphs each have some discontinuities, and so we want to talk about which one of those rules above has been violated. So of course this one has a hole. I would have to lift up my pencil and then actually go back and make that hole. So of course it violates rule number 1 because it's not defined at f of c. And when we talk about can we remove this, yes, I could fix this. It'd be a real easy fix. All I'd actually have to do is just color it in, and now I have a continuous curve. The second one has a jump. I have to literally pick up my pencil and move it, so it violates rule number 2, and it's not removable because even if I try to fill in a bubble, I still have the jump, so there's no way for me to really fix it. The whole reason, just sort of as backup, that it violates this rule number 2 is if I look at the limit as I approach from the left, so approaching c from the left, it does not equal the limit as I approach c from the right. So remember, I'm using that negative to indicate that I'm approaching from the left, right here, and this one telling me I'm approaching from the right. So as I move in from the left, I'm getting closer and closer to wherever this value is, versus when I move in from the right, I'm getting closer and closer to this value, and those, of course, are not equal. And this last one has what we call a gap because it is actually defined at c. So I know an actual y value when x is c. The actual y value is right there at that dot. And so this one violates rule number 3. And again, it is removable if I take that dot and simply push it up so that it will fill in that spot. So I could fix that one. And of course that one violates because the limit as x approaches c does not equal f of c. Okay, and then the next example, that's kind of messy, but I think you heard me just say it. So the next example is a infinite, discontinuity because it has an asymptote, and that goes forever. And so this one violates both rule number 1 and number 2 because from the left and right are not equal, and also because at this point, whatever it happens to be, let's call it c, f of x is not defined. There's no actual y value because it just goes on forever and ever and ever. And this one also is not removable. There's no quick fix like there is on the other ones where I can just move the dots or shade in the dots. And so as you noticed, when the limit does not exist, there's either a removable jump or there's a vertical asymptote.